Everyone, I just wanted to make this short video to show you how to do one of the problems that we were supposed to do for last Saturday's homework, and also just show you how to manipulate Marvin a little bit if you're wanting to make it look a certain way or something like that. So, I mean, hopefully you've watched the Marvin tutorials and they're great, but this will just maybe add a little bit more information in there. So let's look at the homework. All right, so this problem was the last one in Saturday, or the last regular problem, and there are a couple more. So problem 1.66 in the homework that was due on Saturday. And the question says, write a Lewis structure for this cation. It's the isopropyl cation up here, including formal charge. If there are any electrons around any of the atoms, the details will be addressed in the next section. So for one, that's been causing people fits, is that some of these early problems are not asking you to actually put the two lone pair electrons around atoms. So that is in the correct Lewis structure, but they're just wanting you to basically sketch out the skeleton of the molecule to begin with, and then go from there. So let's go ahead and click edit here, and we can get started. That really won't be a huge issue here. The first thing is making sure we know what we're drawing. So before you can start drawing the correct molecule, let's make sure we understand what this thing is right here. So first off, this is a condensed structural formula. So you've probably seen these before, but I don't know if you may not remember how that works. So what they're saying is there's CH3, there's a carbon connected to 3 hydrogens, and there's 2 of them. So if you were to list it out, there's this CH3 that has a positive charge on it, a CH that has gonna have a positive charge on something here, and then there's a CH3 connected to it and another CH3 connected to it. So if you're trying to add up how many total electrons are in this, you start with the atoms, right? That there's 3 carbon atoms, and that there's 1, 2, 3, 4, 5, 6, 7 hydrogen atoms, and then this whole molecule is going to have a positive charge. So carbons have 4 valence electrons times 3. Hydrogens have 1 valence electron times 7 atoms. And this positive charge means that an electron, a negatively charged electron, has been removed from this molecule. So there you're going to subtract 1 electron. When you add it all up here, 4 times 3 is 12, plus 7 minus 1 is going to get you 18 total valence electrons. So if I were doing this by hand, you draw out the molecule skeleton, you'd put like a carbon here. Doesn't really matter how you orient this right now. A carbon here, maybe a hydrogen down here, carbon, the carbon up here and down here are the ones that have the hydrogens attached to them. So you'd put 3 hydrogens attached. Three hydrogens attached down here. And this is pretty much what the problem was saying. Hey, don't worry about any extra electrons here. Just go ahead and connect everything and roll with it. But there's a few things that I want to point out here, and one thing that we're really kind of missing here. First off, let's go ahead and count the electrons anyway. So each bond counts for 2 electrons. I'll switch colors here just so you can see I've counted them. So each covalent bond is 2 electrons shared between atoms. So that bond is 2 electrons. This bond is 2 electrons. This bond is 2 electrons. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So that's actually already our 18 electrons. So we actually have put in every electron we need to in the structure. And then last, there's the issue of this positive charge. Where does that go? Well, you can leave it out of Lewis structure sometimes. I think you used to see in your previous classes, sometimes we'd put brackets around something and put a positive charge out here. That's not wrong now, but we like to bring that positive charge into the structure as a formal charge. So you can see which atom has the formal charge here. The carbon, which we know carbon had the original 4 valence electrons. There were 1, 2, 3, 4 valence electrons. So it's pretty easy to spot that this carbon here in the middle is not bonded to 4 different things. So that must be the one that has the formal charge. And you can add it up carefully if you want through the standard method of doing that. But we'll bring that charge from the outside usually in and make it a formal charge in the Lewis structure. This is the more typical way to do it in organic chemistry. So that brings us up to date on what it is we're going to be trying to draw there. Now, how do we go about actually drawing that molecule in? So let's clear out the screen and use Marvin's sketch. So the first thing to do is you just generally click on an atom. Oh, I got to get out of this. There we go. Like carbon, you just start connecting them together. So you just click it there and that's going to put a carbon. If you click on that carbon and drag, it'll add another carbon. And if you click on that carbon and drag, it'll add another carbon. So you notice a few things here. First off, when we were drawing the carbons, we were drawing the bonds out to all the hydrogens, as well as drawing C's every place there was a carbon. And here you can see it actually took away the letter C. So this is a common way of drawing molecules in organic chemistry to save ourselves some time, that we know that hydrogens spread out evenly around carbons, so we don't have to show where they're all at. We're going to get bigger and bigger molecules here, so it's going to be really annoying to show where every hydrogen is. So I like to just draw them collapsed around a carbon. And also, if we know there's a big chain of carbons, we don't like to draw a C in every location. So just we know that every angle, there's a C there. So we'll be studying this in detail coming up, how this works. But if you don't want to do this right now, you don't have to do this. It's just that Marvin knows that this is a common way of drawing in organic chemistry. So if you don't like this right now, you don't have to work with it on Marvin, but it is a bit of a pain. The way you deal with it is, first off, the hydrogens. Just grab the H and draw those in, and you're perfectly welcome to get those drawn in everywhere there should be an H attached here. So now we've got all the H's and all 7 H's. And the only thing left that we really hate about this is that it's not actually showing the carbons. So that's a little bit more of an annoyance. You have to right click to bring up the context menu, and then go to atom properties. And if there's another way to do this in this version of Marvin, I don't know how. So this is the way I'm showing to do it. Alias is what it's actually going to display there. So just click unlock for that cell and put a C there. Say okay, and you're just going to have to go 1 carbon at a time, unlock atom properties, unlock alias, type a C there. Okay. And being able to right click and bring up this context menu is a really nice thing in Marvin. So that's a lot of why I wanted to show you this, that it gives you a lot of functionality that you can control about an element. So that's it for now. We've got all of our carbons, all of our hydrogens. It looks about like what we want. The only last thing that we would need to do is add a positive charge there. And you could do that by clicking this and then clicking on the atom. It'll put the positive charge there. The other way to do it is to right click and say atom properties and actually type a charge in, that it has a positive charge. Otherwise, if you don't do that, it's going to think it has that extra electron. It might even think that extra electron is bonded to a hydrogen. Marvin's very predictive, which in the long run in this course is going to be great. But when you're first interacting with it, you're going, what is going on with this stuff? So you just do that. If you were needing to have a single electron, you could choose radical here. Monovalent would mean there's 1 single electron. Divalent would be 2 single electrons, not paired in a lone pair. And this is where you can do a lot of those features from here. So I'm just going to put a charge there. I'm sorry, you'd use the numbers there, not positive. Use positive numbers or negative numbers, depending on the size, whether the charge is positive or negative. Say okay, and it's going to put, it does know there's a positive charge. I don't know why we're not seeing it right now, but it does know, I think, because if you open it back up again, it does know there's a positive charge there. So, okay, nothing's changed. I'll just close it out. And now if you say close, you will be able to see that positive charge there. So that is the correct Lewis structure. I haven't submitted this, so let's go ahead and see if it actually accepts it as the correct answer. Yes, it did. It should have, because we know that's the correct Lewis structure. So perfect. So that's just an idea of how you can go about interacting with Marvin and really bending it to what you want it to look like, instead of just accepting the way that it naturally snaps into looking. So hopefully that was some helpful, and you can use that trick to get what you want out of Marvin sketch.